The morning of July 5, 1942, Lieutenant Commander Eddie Sanders stood on the tarmac at Naval Air Station San Diego, staring at something that should not have existed on American soil. Before him sat a Mitsubishi A6M Type 0 fighter, its cream-colored underside still streaked with Aleutian mud, the red Hinomaru insignia stark against pale grey wings. The aircraft rested on a flatbed trailer, its propeller bent, landing gear collapsed, but otherwise remarkably intact. Sanders had flown against Zeros over the Coral Sea just 2 months earlier. He had watched them slice through American formations with a grace that seemed to mock physics itself. He had seen good men die because they could not turn with these machines, could not climb fast enough, could not escape the methodical pursuit of Japanese pilots who flew aircraft that seemed born of some engineering philosophy Americans did not yet understand. Now one sat before him, captured, silent, waiting to reveal its secrets. The Zero had arrived 3 days earlier, transported by ship from the Aleutian island of Akutan, where it had been discovered nearly intact in a muskeg bog. The pilot, Petty Officer Tadayoshi Koga, lay dead in the cockpit when the American recovery team found him in mid-July, his neck broken from the impact of the forced landing. His body had been buried with military honors on Akutan. His aircraft had been crated and shipped south to be reborn as America's most valuable intelligence asset of the Pacific War. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Sanders circled the Zero slowly, notebook in hand. The aircraft measured just under 30 feet in length, with a wingspan of 39 feet. It weighed, according to the initial assessment, approximately 5,300 pounds empty. His own Grumman F4F Wildcat weighed nearly 6,000 pounds, empty, and that was before accounting for armor, plating, and self-sealing fuel tanks, equipment the Zero conspicuously lacked. He knelt beside the wing, running his hand along the aluminum skin. It flexed slightly under his touch, thinner than American specifications would ever permit. The entire aircraft seemed built according to a different calculus, one that prized speed and maneuverability above all else, that accepted vulnerability as the price of performance. The question that had haunted American naval aviation since the Battle of the Coral Sea, since the raid on Pearl Harbor, since every engagement where Zeros had appeared, was deceptively simple. How do you fight something you cannot catch, cannot outmaneuver, cannot escape? Every tactical manual, every after-action report, every debriefing of surviving pilots pointed to the same conclusion. The Zero was superior in nearly every measurable way. It could turn inside any American fighter. It could climb faster. It could operate at ranges that seemed impossible. Japanese pilots launching from carriers could escort bombers hundreds of miles to target and return, while American fighters struggled to provide even local air defense. The prevailing doctrine among American fighter pilots had become one of grim acceptance. You did not dogfight with Zeros. You did not try to turn with them. You used speed and altitude, diving attacks and quick escapes, and you hoped that numbers and determination might overcome technical inferiority. It was a doctrine born of necessity, of survival, of watching too many friends spin into the ocean trying to match a Zero turn for turn. But now, Sanders thought, now we have one. Now we can learn. The Zero's reputation had been carefully cultivated long before the first bombs fell on Pearl Harbor. In the skies over China, beginning in the summer of 1940, Japanese naval pilots flying the newly deployed A6M had achieved kill ratios that seemed fantastical. Chinese pilots flying Soviet-built Polikarpov I, 16 seconds, and Ioni 153 seconds. American-supplied Curtiss Hawks, even the occasional captured Japanese aircraft pressed into service, fell before the Zero in numbers that reshaped tactical thinking across the Imperial Japanese Navy. By the time war came to the Pacific in December 1941, the Zero had destroyed an estimated 99 Chinese aircraft for the loss of only 2 Zeros in air combat over a period of 18 months. These were not exaggerations or propaganda inflations. They were verified tallies, documented by both Japanese and Chinese records, witnessed by American advisors and journalists who watched the one-sided engagements from the ground. The aircraft had earned its mystique honestly, through technical excellence and pilot skill combined in proportions that no other nation had yet achieved. American intelligence knew the Zero existed. Claire Chennault, commanding the American volunteer group in China, had warned Washington repeatedly about the Cote aircraft's capabilities. His reports, detailed and urgent, described an enemy fighter that could outperform anything in the American inventory. But intelligence reports and combat reality occupy different spaces in military consciousness. It was one thing to read that the Zero could turn inside a Curtiss P-40 Warhawk. It was another thing entirely to experience it, to pull back on the stick with all your strength and watch a Zero slide effortlessly onto your tail anyway, to realize with sudden visceral certainty that your aircraft would not save you, that only luck or intervention might. The shock of Pearl Harbor included, for American pilots who survived the initial attack, their first encounter with an aircraft that seemed to operate according to different physical laws. Zeros from the carriers, Akagi, Kaga, Soryu, Hiryu, Shokaku, and Zuikaku, swept aside what little aerial resistance materialized, destroying American aircraft on the ground and in the air with an efficiency that spoke to both superior equipment and superior training. In the months that followed, as war spread across the Pacific, the pattern repeated. At Wake Island, at Rabaul, at Port Moresby, in the skies over Java and Sumatra and the Philippines, the Zero demonstrated again and again that it represented not just an incremental improvement over previous Japanese designs, but a fundamental leap forward in fighter aircraft capability. The aircraft's technical specifications, pieced together from pilot reports and crashed examples, painted a picture of engineering priorities that diverged sharply from American practice. The Sakai 12 radial engine, producing barely 940 horsepower, somehow pushed the Zero to speeds exceeding 330 miles per hour. The wing loading, a measurement of aircraft weight divided by wing area, was extraordinarily low at just under 17 pounds per square foot, compared to nearly 27 pounds per square foot for the Wildcat. This meant that the Zero needed less speed to generate the same lift, could turn more tightly, could maintain control at speeds that would stall American fighters. Japanese engineers at Mitsubishi had approached the Zero's design with a clarity of purpose that American designers, constrained by different institutional pressures and tactical assumptions, had not matched. The specification, issued by the Imperial Japanese Navy in 1937, demanded an aircraft that could escort bombers on missions exceeding 1,000 miles, that could outmaneuver any existing fighter, that could operate from aircraft carriers, and that could achieve a maximum speed of at least 310 miles per hour. These requirements seemed mutually exclusive. Range demanded fuel capacity and weight. Maneuverability demanded lightweight and low wing loading. Carrier operations demanded structural strength and low landing speeds. Speed demanded power and streamlining. The solution, devised by chief designer Jiro Horikoshi, was to eliminate everything not absolutely essential to the mission. Armor plating that might protect the pilot, eliminated. Self-sealing fuel tanks that might prevent fires, eliminated. Redundant control systems, heavy radios, even basic amenities that Western designers considered standard. All eliminated. The fuselage skin was rolled to the minimum thickness that could maintain structural integrity. The wings used a revolutionary construction technique that reduced weight while maintaining strength. Every component was scrutinized for potential weight reduction. The result was an aircraft that weighed barely half what its American contemporaries weighed, that could fly nearly 2,000 miles on internal fuel, that could turn inside any Allied fighter in service when the Pacific War began. It was a masterpiece of weight optimization, of purposeful engineering, of accepting certain vulnerabilities in exchange for overwhelming advantages in other areas. Japanese naval aviation doctrine assumed that air superiority would be achieved through technical excellence and pilot skill, that the best defense was to shoot down the enemy before he could shoot you, that battles would be decided by maneuverability and range rather than by attrition and armor. This philosophy had deep roots in Japanese military culture. The samurai tradition emphasized offense over defense, accepted death as preferable to dishonor, valued the individual warrior's skill above mechanical protection. These were not mere cultural affectations imposed on modern warfare. They were conscious choices, reflected in training methods that were brutal and unforgiving, that produced pilots who could fly for 8 hours in cramped cockpits without complaint, who could navigate by dead reckoning across featureless ocean, who could execute aerobatic maneuvers that would incapacitate Western pilots not conditioned to sustained high G-forces. American pilots facing Zeros, in early 1942, were not merely confronting superior technology. They were confronting a completely different conception of what air combat should be, what a fighter aircraft should prioritize, what risks were acceptable in pursuit of victory. The Zero embodied a philosophy that regarded pilot safety as secondary to mission accomplishment, that assumed air combat would be decided in the first decisive engagement rather than through sustained operations, that believed a lightweight, long-range, highly maneuverable fighter, flown by a superbly trained pilot, represented the ultimate expression of naval air power. And for the first 6 months of the Pacific War, this philosophy appeared vindicated by results that suggested Japanese technological and tactical superiority across the board. The Zero that arrived at Naval Air Station San Diego had traveled a circuitous route from its final resting place. On June 4, 1942, during the opening phase of the Battle of Midway, the Japanese had launched a diversionary attack on Dutch Harbor in the Aleutian Islands. Petty Officer Tadayoshi Koga, flying from the carrier Ryujo, participated in the strike. During the engagement, American anti-aircraft fire damaged his Zero, severing an oil line. Koga attempted to return to his carrier but realized he would not make it. He chose instead to make an emergency landing on Akutan Island, a small, uninhabited volcanic island about 25 miles from Dutch Harbor. The island offered what appeared to be a suitable landing site, a relatively flat area covered in low vegetation. What Koga could not see from altitude was that the flat area was actually a muskeg bog, a wetland formed of partially decayed vegetation and standing water covered by a deceptive layer of grass. When his wheels touched down, they immediately sank into the soft ground. The aircraft flipped forward, inverted, trapping Koga in the cockpit. The impact broke his neck instantly. His Zero remained there, upside down in the bog, hidden from casual observation by the tall grass surrounding it. On July 10, 1942, more than a month after Koga's crash, a U.S. Navy PBY Catalina, flying a routine patrol, spotted the wreckage. A recovery team was dispatched immediately. What they found astonished them. A Zero fighter that was essentially intact, damaged only by the forced landing and subsequent inversion. The aircraft had landed in soft ground that cushioned the impact. The cold Aleutian climate had preserved it. The remote location had kept it hidden from Japanese search efforts. The recovery operation required careful planning. The team carefully excavated around the aircraft, built a platform beneath it, then used jacks and pulleys to right it. They removed the wings and disassembled other major components for transport. By late July, the Zero was crated and loaded aboard a ship bound for San Diego. The entire operation was conducted under strict secrecy. Japanese forces still controlled several Aleutian islands. If they learned that an intact Zero had been captured, they would certainly attempt to destroy it. At San Diego, a team of engineers and test pilots began the painstaking process of restoration. They replaced the bent propeller with one fabricated to match the original specifications. They repaired the landing gear. They patched bullet holes from the Dutch Harbor engagement. They drained the fuel system and refilled it with American aviation gasoline to see if the engine would tolerate the different formulation. Japanese aircraft used fuel with different octane ratings and additives than American fuel. There was genuine concern that the sake engine might not run properly on American supplies. On September 20th, 1942, nearly 4 months after Koga's death, Lieutenant Commander Eddie Sanders climbed into the Zero's cockpit for the first time. The seat was cramped, designed for the smaller average stature of Japanese pilots. The instrument panel was labeled entirely in Japanese characters. The control layout was unfamiliar, reversed in some cases from American conventions. But the basic flight controls, the stick and rudder pedals, were universal. Sanders ran through the pre-flight checklist, translated laboriously by Navy intelligence officers who had studied the aircraft's manual, recovered from another crashed Zero. The Sakai engine coughed, sputtered, then caught with a sound distinctly different from American radial engines, higher pitched, smoother, almost refined. Sanders taxied to the runway, feeling the aircraft's responsiveness through the controls. The Zero required almost no pressure to turn on the ground. The tail lifted immediately as he advanced the throttle for takeoff. At 60 miles per hour, the aircraft simply floated off the runway, climbing away with an eagerness that felt unnatural compared to the Wildcat's more ponderous departure. Within minutes, Sanders understood viscerally what every pilot report had tried to convey. This aircraft operated in a different performance envelope entirely. Sanders spent the next 2 hours exploring the Zero's flight characteristics systematically. He climbed to 10,000 feet and performed a series of turns, increasing the bank angle progressively. The Zero turned effortlessly, tightening its radius without the buffeting or stall warnings that would have appeared in American aircraft at similar angles of attack. He could pull the stick back firmly, and the Zero simply turned, the controls remaining light and responsive throughout. At 20,000 feet, he performed the same exercise. The results were identical. The Zero maintained its maneuverability at altitude, where American fighters became increasingly sluggish. He tested the climb rate, pushing the throttle forward and pulling the nose up at various angles. The Zero climbed at over 3,000 feet per minute at sea level, nearly double the Wildcat's initial climb rate. Even at 15,000 feet, where air density decreased significantly, the Zero continued climbing at rates that would allow it to dominate the vertical dimension of combat. Sanders understood immediately why American pilots reported feeling helpless against Zeros in climbing engagements. The Japanese fighter simply went up faster, could sustain steeper angles, could reach advantageous altitudes before American aircraft could respond. Then Sanders began testing high-speed maneuvers. He pushed the Zero into a steep dive, watching the airspeed indicator climb past 250 miles per hour, past 300, approaching 350. At that speed, he attempted a sharp turn to the right. The control stick suddenly became heavy, resistant to his input. He applied more pressure. The stick moved, but sluggishly, and the aircraft's response was delayed, mushy. He tried rolling left at the same speed. The result was even worse. The ailerons, the wing-mounted control surfaces that governed roll rate, barely responded. The Zero wallowed through the roll attempt like a transport aircraft, not a fighter. Sanders reduced speed and tried again. At 250 miles per hour, the roll response improved but remained noticeably sluggish compared to the aircraft's performance at lower speeds. At 200 miles per hour, the characteristic lightness returned. He repeated the test multiple times, at different altitudes and speeds, confirming what his initial discovery suggested. The Zero had a critical limitation in high-speed maneuvering, specifically in roll rate. The explanation lay in the aircraft's design philosophy. To achieve low weight and high maneuverability at combat speeds below 300 miles per hour, Mitsubishi's engineers had used relatively light wing structures and fabric-covered control surfaces on the ailerons. At lower speeds, this design worked perfectly, providing the feather-light, control response that made the Zero so maneuverable in dogfights. But at high speeds, aerodynamic forces increased exponentially. The fabric covering the ailerons would actually deform under air pressure, reducing their effectiveness. The wing structure itself would flex, further compromising control authority. The Zero's greatest strengths at typical dogfighting speeds became a profound weakness at the high speeds American pilots could achieve in dives. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Sanders landed and immediately convened a meeting with the test team. He described his findings in technical detail. The implications were discussed at length. If the Zero could not roll effectively at high speed, then American pilots could exploit this limitation through specific tactical maneuvers. A Wildcat could not turn with a Zero at 200 miles per hour, but a Wildcat could dive to 350 miles per hour, and at that speed, it could roll away from a pursuing Zero faster than the Zero could follow. Within days of Sanders's initial test flight, a team of experienced combat pilots arrived at San Diego to fly the Zero and develop specific tactical recommendations. Among them was Lieutenant Commander John Thatch, who had already developed the Thach weave, a defensive tactic where two fighters flew in a coordinated weaving pattern that made it difficult for Zeros to attack either aircraft without exposing themselves to fire from the other. Thatch flew the captured Zero extensively, confirming Sanders's findings and expanding on them. Thatch discovered that the roll limitation became even more pronounced when the Zero attempted to reverse direction quickly. If an American pilot could force a high-speed encounter, then suddenly roll in the opposite direction, the Zero pilot would find himself unable to follow quickly enough. The American pilot aircraft would escape before the Zero could reorient. This was revolutionary. For the first time since the war began, American pilots would have a reliable method for escaping Zero attacks, a technique based not on hope or luck, but on documented performance limitations. The Navy's Bureau of Aeronautics immediately began producing training materials. A detailed technical report on the Zero's performance characteristics was compiled, including specific speed ranges where American fighters held advantages. The roll limitation was emphasized prominently. Diagrams showed the recommended escape maneuver: enter a high-speed dive, wait for the Zero to follow, then execute a sharp rolling reversal at maximum speed. The Zero would be unable to match the roll rate, allowing the American pilot to escape or potentially reverse the engagement. More importantly, actual flight training incorporated these findings. At naval air stations across the Pacific, instructors briefed pilots on the Zero's limitations. Some stations received captured Zero aircraft for demonstration purposes. Pilots could see firsthand how the vaunted Japanese fighter became sluggish and unresponsive at high speeds. They could practice the escape maneuver against a real Zero, building muscle memory and confidence. The psychological impact was profound. Pilots who had viewed the Zero as an invincible opponent now understood that it had exploitable weaknesses, that survival was not merely a matter of luck. The Army Air Forces received similar intelligence. Pilots flying P-38 Lightnings, which had excellent high-speed performance and roll rates, were specifically instructed to exploit the Zero's limitations. P-40 Warhawk pilots, flying an aircraft that could not match the Zero in turning combat but could dive fast and roll quickly, received tactical guidance that played to their strengths and the Zero's weaknesses. Even pilots flying the outdated P-39 Airacobra, generally considered inferior to frontline fighters, learned that they could survive encounters with Zeros by refusing to engage in low-speed turning fights and instead using speed and roll rate. The captured Zero continued flying throughout 1942 and into 1943, accumulating hundreds of test hours. Navy pilots used it for training purposes, practicing attacks and escapes against the actual threat they would face in combat. Engineers studied every aspect of its construction, producing detailed technical reports that influenced American fighter design. The lessons learned from Koga's Zero directly contributed to the development of improved American fighters, including the F-6F Hellcat, which combined the Wildcat's ruggedness with performance specifications designed specifically to counter the Zero's advantages while exploiting its weaknesses. By early 1943, the tactical recommendations derived from the captured Zero had permeated American naval aviation doctrine at every level. Pilots arriving in the Pacific Theater received standardized briefings that included specific guidance on engaging Zeros. Maintain speed above 300 miles per hour whenever possible. Avoid sustained turning engagements below that speed. Use altitude advantage to control engagement parameters. Exploit the roll rate limitation through high-speed reversals. These were not suggestions or experimental tactics. They were codified procedures, tested against the actual aircraft, verified by pilots who had flown both the Zero and American fighters in controlled conditions. The impact became measurable in combat results. During the Guadalcanal campaign, which began in August 1942, American pilots initially suffered significant losses against Zeros operating from Rabaul. But as the campaign progressed and more pilots received training based on the captured Zero's limitations, the loss ratios began shifting. Marine pilots flying Wildcats from Henderson Field learned to work, in pairs, using the thuh weave and high-speed tactics to negate the Zero's turning advantage. They avoided the low-altitude, low-speed dogfights where Zeros excelled. They used their aircraft's superior diving speed and roll rate to dictate engagement terms. Navy pilots aboard carriers received similar training. The battles around the Solomon Islands throughout late 1942 and early 1943 demonstrated the effectiveness of these new tactics. American pilots were still flying aircraft that were technically inferior to the Zero in many respects. The Wildcat remained slower in level flight, climbed more poorly, and could not match the Zero's turn radius. But American pilots now fought according to tactics that minimized these disadvantages while exploiting the Zero's specific weaknesses. They survived encounters that would have been fatal months earlier. They scored victories against aircraft that had previously seemed untouchable. The introduction of new American fighters accelerated the shift. The F-6F Hellcat, which entered service in January 1943, incorporated lessons learned directly from studying the captured Zero. Its designers knew precisely what performance characteristics were necessary to compete effectively. The Hellcat could not turn as tightly as a Zero at low speeds, but it could dive faster, roll more quickly at high speeds, and absorb battle damage that would destroy a Zero. More importantly, Hellcat pilots received comprehensive training on Zero tactics and limitations before they ever encountered one in combat. They understood the threat intellectually before facing it physically. The Vought F-4U Corsair, entering service around the same period, offered even more pronounced advantages in speed and high-altitude performance. Corsair pilots could engage Zeros at speeds where the Japanese fighters' controls became ineffective, could climb away from pursuits using superior power-to-weight ratios at altitude, could execute rolling maneuvers that Zeros simply could not follow. The tactical doctrine remained consistent. Avoid the Zero's strengths, exploit its weaknesses, use superior training and coordinated tactics to overcome individual aircraft limitations. By mid-1943, the air combat situation in the Pacific had fundamentally reversed. Japanese pilots, many of them the experienced veterans who had achieved such dominance in early 1942, found themselves facing American pilots who no longer flew predictably, who refused to fight on Japanese terms, who exploited every weakness in the Zero's design. The kill ratios that had so favored Japan in the war's first year began tilting the other direction. American pilots were not just surviving encounters with Zeros, they were winning them consistently, methodically, using tactics derived from hundreds of hours of test flights in Tadayoshi Koga's aircraft. The myth of Zero invincibility, built carefully over years of combat in China and months of dominance in the early Pacific War, shattered against the reality of informed tactical adaptation. The captured Zero represented more than a tactical windfall. It demonstrated the broader importance of technical intelligence in modern warfare. American efforts to recover and analyze enemy equipment intensified throughout 1943 and 1944. Every crashed Japanese aircraft that could be retrieved was examined in detail. Reports from these examinations were compiled and distributed throughout the Pacific theater. Pilots learned not just about the Zero, but about the Nakajima Ki-43 Oscar, the Kawasaki Ki-61 Tony, the Mitsubishi J2M Raiden. Each aircraft had specific strengths and weaknesses. Each could be defeated by pilots who understood its limitations. Japanese intelligence efforts did not achieve similar systematic success. While Japanese forces captured American aircraft throughout the war, they never established the places, comprehensive testing and dissemination programs that characterized American technical intelligence. Part of this disparity reflected institutional differences. American military culture emphasized standardized training and widespread information distribution. Japanese military culture maintained stricter hierarchies and more restricted information flow. Tactical lessons learned by one unit might never reach others. The advantages gained from studying captured equipment might benefit a small number of elite pilots, but would not necessarily influence broader training programs. The cultural factors extended to aircraft design philosophy as well. As the war progressed, American fighters incorporated increasingly heavy armament, armor protection, and robust construction. The F-6F Hellcat could absorb tremendous battle damage and return to carrier. The F-4U Corsair could survive hits that would have been catastrophic to lighter aircraft. These design choices reflected American industrial capacity and tactical priorities. Aircraft could be replaced more easily than trained pilots, therefore protecting pilots justified additional weight and complexity. Japanese designers continued prioritizing light, weight, and maneuverability, even as these priorities became increasingly problematic. Later variants of the Zero added some armor protection and self-sealing fuel tanks, but these additions compromised the aircraft's fundamental performance advantages without bringing it to parity with American standards of survivability. The A6M variant, introduced in 1943, had slightly better high-speed handling than earlier versions, but still could not match American fighters in roll rate at combat speeds. Japanese pilots continued flying aircraft that could be destroyed by single hits to fuel tanks or control systems that offered minimal protection against the increasingly heavy armament of American fighters. The disparity in pilot training programs compounded these equipment differences. American training programs expanded dramatically after Pearl Harbor. Flight schools produced thousands of pilots annually, each receiving hundreds of hours of training before entering combat. The training included extensive gunnery practice, formation flying, tactical doctrine, and specific guidance on engaging different enemy aircraft types. Pilot quality remained consistently high throughout the war because the training pipeline continued producing well-prepared replacements for combat losses. Japanese training programs, constrained by fuel shortages and prioritizing quality over quantity, produced fewer pilots with increasingly abbreviated training as the war progressed. The experienced pilots who had dominated the war's early months were irreplaceable. As they were lost to combat, accident, and attrition, their replacements lacked both the flight hours and the tactical experience necessary to compete effectively. By late 1943, American pilots often faced Japanese opponents who had only basic flight training, who had never practiced the complex aerobatic maneuvers that had made early Japanese pilots so formidable, who were flying aircraft whose limitations they did not fully understand because the sophisticated training programs that had produced earlier generations of pilots no longer existed. The captured Zero's contribution to this shifting balance cannot be quantified precisely. No single piece of intelligence, no matter how valuable, determines the outcome of conflicts as large and complex as the Pacific War. But the aircraft provided American forces with critical knowledge at a crucial moment. It transformed the Zero from an incomprehensible threat into an understood opponent. It gave American pilots specific, actionable tactics that saved lives and increased combat effectiveness. Tadayoshi Koga's death on Aleutian Island was recorded in Japanese records as a combat loss, circumstances unknown. His family received notification that he had died in service to the emperor, that his sacrifice honored Japan, that his name would be remembered. They were never told that his aircraft had been captured intact, that American pilots had studied it exhaustively, that the intelligence derived from his Zero had contributed to the deaths of thousands of Japanese pilots who faced American aircraft flown by men who understood exactly how to exploit the weaknesses Koga's aircraft revealed. The moral complexity of this outcome deserves acknowledgement. Koga was 21 years old when he died, a skilled pilot serving his country in a war he had not chosen to start. The intelligence value of his aircraft came at the cost of his life and eventually contributed to the deaths of his comrades. War creates these grim ironies. One man's misfortune becomes another nation's advantage. Individual tragedy enables collective victory. Death feeds intelligence that produces more death. The captured Zero flew its last test, flight in February 1945. By that point in the war, its intelligence value had been thoroughly extracted. Newer Japanese aircraft had entered service. The tactical lessons derived from Koga's Zero had been incorporated into standard training for years. The aircraft itself, worn from hundreds of test flights and training demonstrations, was no longer airworthy enough to risk further flights. It was placed in storage, a museum piece, an artifact of how completely the air war's dynamics had shifted since that morning in July 1942 when Eddie Sanders first climbed into its cockpit. The broader legacy extends beyond tactics and kill ratios. The systematic study of Koga's Zero established precedents for technical intelligence that influenced American military practice throughout the Cold War and beyond. The principle that understanding enemy capabilities required not just observing them in combat, but actually testing captured equipment, became foundational to American intelligence doctrine. When the Soviet Union's most advanced fighters appeared over Korea in the 1950s, American forces made intensive efforts to acquire examples for testing. When new weapon systems emerged during subsequent conflicts, recovery and analysis followed established procedures refined during World War II. The story that began with a damaged Zero crashing into an Aleutian bog ultimately touches on fundamental questions about how wars are won. Superior numbers matter, industrial capacity matters, but knowledge matters as well. Understanding the enemy, comprehending not just what he can do but why he can do it, and where his capabilities end, provides advantages that can overcome significant material disadvantages. American pilots in early 1943 were still flying inferior aircraft by many measures, but they were flying them intelligently, exploiting known weaknesses, avoiding known strengths, fighting according to doctrine derived from rigorous testing rather than desperate improvisation. Tadayoshi Koga's grave remains on Akutan Island, a simple marker maintained occasionally by Japanese and American veterans groups who understand that individual soldiers deserve respect regardless of which flag they served. His Zero, or what remains of it after years in storage, resides in a restoration facility, being prepared for eventual museum display. The aircraft that killed him, the American guns that damaged his oil line over Dutch Harbor, have long since been scrapped or lost to history. What persists is the lesson his unintended contribution taught: that understanding enemy capabilities transforms impossible odds into survivable engagement, that knowledge derived from careful study outweighs assumptions based on propaganda or fear, that the simple act of turning an enemy's strength into documented, exploitable limitation can shift the trajectory of entire campaigns. Every American pilot who rolled away from a pursuing Zero at high speed, who survived because he understood the limitation in that fabric-covered aileron, who returned to his carrier because someone had taught him that the invincible enemy aircraft had specific, exploitable weaknesses, owed a portion of that survival to an intelligence windfall born from one pilot's forced landing in a remote Aleutian bog. The math of war is never simple, but sometimes it includes a Japanese pilot's final flight becoming the foundation for tactics that saved thousands of his enemies' lives while ending thousands of his comrades. History offers no resolution to this irony, only acknowledgement that war creates these intersections, where individual fate and collective outcome collide with consequences that echo across decades. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.